This talk I've given several times now. I've given it as a lecture. I've given it at a conference or a meeting, what have you. I've given it internally. And every time I give this talk, it always springs discussions. Mostly because this idea of porting Fortran codes to GPUs is one that people are going through right now, or they just went through, or they're about to go through, and it's one that people want to share their war stories, or they want advice as they go along the way, or advice before they start, or what have you. And always it's like a really impassioned discussion, typically after the talk is given, about all of the different aspects and decisions and things that you have to make to get this done. And that's why I thought it would be a really good topic to cover in a more public forum such as this, and have it recorded so people can be referred to it back in the future. So before we get into the nitty-gritty details of the meat of this presentation, the first thing I have to do is evangelize our group a little bit. I work for the Numerics Research Group at the Institute of Aerodynamics and Gas Dynamics at the University of Stuttgart. As our name suggests, our primary research interests are numerical methods, predominantly for large eddy simulation and direct numerical simulation for CFD. And because we're interested in such things, we also are very interested in software techniques and methods and things for CFD in the high performance computing space. We have to be, or we wouldn't be able to do our research. We have many codes, but the two of our codes that will concern us today are FLEXI and GALÆXI. Both are a high order discontinuous Galerkin spectral element method. Theoretically, these codes can do any equation set, but we almost entirely internally use them for the compressible Navier-Stokes equations. FLEXI is the original version of this code. It's 10 plus years old, I think. I honestly don't know how old, far before my time with the group. It is a CPU only, all Fortran code. And GALÆXI, which I will give more detail on later, far more detail, is the new GPU accelerated version of this code. If you're interested at all in what we're into right now, what we have going on, like news, who we are in more detail, other things we're interested in research-wise, this little QR code will take you to our website where you can find all of that information. I'm going to skip on now. If you can't grab that QR code while I'm talking, I'll have it up the entire time we're answering questions later. So this talk is framed from a point of view of someone who has a CPU-only Fortran scientific code. I say scientific, it's going to be predominantly toward things like CFD or related discretized grid computational disciplines, things like computational electromagnetics, structural mechanics, things like that. You also might have a Fortran code that runs on a single vendor of GPU, but you want this Fortran code to run on GPUs and or more than one vendor of GPUs. Perhaps you have one that runs only on AMD or only on NVIDIA or what have you. And also your code can't use what I'll call an off-the-shelf solution. So this means like codes I've worked on in the past, they construct a giant matrix. You find the eigenvalues of this matrix with a scala-pack or a BLAS call, and then you use those eigenvalues to compute all of your properties of interest, right? Code like that, there's libraries that are GPU ported for you already that you can look at, right? And perhaps you don't have to go through all of this process that I'm going to talk about today. So we're orienting this toward the other people who have to go in and manually write their GPU kernels and port their code themselves. Also, I'm going to do the first 20-25 minutes of this is going to be a very shallow skim over some concepts in GPU computing, specifically GPU software as it relates to CUDA/HIP-C++. I'm assuming that you have at least some introductory knowledge to GPUs. If you don't, what I go over will be not enough for you, but it will be something, I guess, and it will provide introduction to terms and things that you can then build off of later, and at least you'll kind of understand what I'm talking about when I get to the explanations of how we do things in GALÆXI. So again, the first part of this is going to be that overview of GPU computing. The idea of this is basically to, again, introduce terms and also kind of nail in some possible problems and questions that we have to tackle and answer in a porting process. And then the second part of this is going to be me enumerating all the ways that we solve these problems and answer these questions in GALÆXI, as hope to serve as an example for a way this can be done for other people. All right. My notes say take a drink of water. Where's my water? All right. And we're going to get into, again, what is a very, very brief overview of some important concepts from GPU computing to serve as a preface to later discussions. So you'll see a lot in GPU hardware descriptions, this idea of cores. And you see it also in CPUs. And this is the primary difference between CPUs and GPUs, is that CPUs have a few very complex cores that are used to do a few things at once, usually. And these things that the CPUs are doing, they're very, very complex, typically a lot of logic, a lot of data movement, a lot of stuff like that. GPUs are the flip side of this coin. GPUs are going to be doing many, many simple things concurrently. And this is reflected in the GPU hardware or GPU cores. The circuitry in them is much, much simpler. When we start flipping over into the software side of thing after this slide, you'll hear a lot about threads. On a GPU, one core is one thread. This is not true for CPUs anymore. Any more CPUs have 2 threads per core, sometimes 4. I don't think any more than that now, but for GPU, one core is one thread. I'm not going to talk about cores anymore. I'm only going to be talking about threads. But no, again, when I'm talking about threads, I'm talking about cores on a GPU. From a hardware perspective, we can bundle a bunch of threads together. And the GPU hardware calls this a warp on NVIDIA or a wavefront on AMD. It's annoying that there's 2 different terms. This problem isn't going to go away. Trust me, they use different terms for basically everything. I'm going to call it a warp from now on. I was raised on NVIDIA GPUs, and that's how I'm going to think about things and denote things going forward. An important thing to remember if you're kind of tackle this multi-vendor problem that we're kind of framing here, warps are different sizes for NVIDIA. So the hardware on NVIDIA GPUs groups threads into 32 by 32s, and it's 64 for AMD. Warps are something that you as a programmer don't have any control over at all. This is a hardware concept. The hardware generates warps. The hardware schedules in warps. And you cannot change the number of threads in them. You can't do anything like that. So the reason I bring this up only is because it's a concept that will kind of be built upon later. And also to remember a very important thing, the most important thing about warps is that when you ask for a certain amount of resources on a GPU, you will always get the full warp. So if you have a problem size of 30 grid points, you will get 32 threads. That it can only work in blocks of either 32 on NVIDIA or 64 on AMD. Now, I could go much, much deeper into the GPU hardware. If that was the case, I would spend the entire hour talking about that. This is not a presentation on GPU hardware, it's a presentation on GPU software. So I'm going to switch into that conversation now. So GPU software, we also have a term called the thread. And thankfully, this is the same as the hardware. When we think about GPU software, we think about threads, multi-threading. A software thread and a hardware thread are the same thing. A thread on a GPU is a single stream of execution that is executing completely independently of all other threads in an operation. We assign an operation to the GPU. It splits the operation into multiple threads, and each of those threads completes that operation completely independently of all the other threads. I'm going to mention this point multiple times in this talk because if you're new to GPU computing, even if you aren't new to GPU computing, this is the hardest thing to wrap your brain around, is this idea that threads are doing things completely independently of one another. Of course, there's exceptions to this, ways that we can force them to communicate, but these, again, are very much exceptions, and you should think of them being complete independent actors. From a software perspective, we can also group threads. And what is the most annoying thing about GPU programming? Both AMD and NVIDIA have a different word for this than on the hardware side. A group of threads on the software is called a block. And I want to be very, very clear here. We talked about warps as a group of threads. A block is not a warp. All right, this confused me. I was working in GPUs for a couple years before I finally actually understood this. Blocks are a software abstraction. Warps are a hardware abstraction. Okay. As the blocks, as a programmer, you have complete control over. You can ask for as many blocks as you want. You can ask for the blocks to be consistent of as many threads as you want. There's, of course, limits and best practices, but theoretically, they can be whatever you want them to be. Okay. Warps, you have no control over. I mentioned that earlier, and I'll reiterate it again. No control over warps. Basically, what we do as a programmer is you request a number of blocks, and then you specify the number of threads in each block. And then the hardware creates the number of warps it needs to meet that requirement that you've specified. Right? So if you ask for 128 threads in 4 blocks, well, that's perfect. It's going to create for you 4 32-thread warps to meet that requirement. Okay? We'll talk about how to specify blocks and block threads per block, and that kind of thing here in a minute. Okay? Before we do that, just I'll mention briefly, there is one level higher of abstraction in this thread grouping concept, and that is a grid. This is all the threads that you've requested for a certain operation, or a kernel, which is a term that I'll get into in a little bit more detail in a minute. Grid, this idea doesn't really usually come up, at least not in terms of what we're going to talk about with GALÆXI. It's just another abstraction that you can use to help when you're maybe doing the conceptual design of your software to map your data to threads. Okay. That was kind of the compute side of the GPU theory you need for the software. The most important thing about GPUs by far is managing memory. This is where you're going to live or die in GPU computing, is managing your memory. There's 3 types of memory that you should be concerned with as a GPU programmer. The lowest level are the registers. These are local to an operation, local to a kernel, right? So a single thread uses registers. There's very limited number of registers, so you have to be very careful about how many you are using, because this is going to be a choke point, especially in memory-bound kinds of software like we are using in computational science. Okay? The next type or next level of memory in GPUs is shared memory. This is a chunk of the caches that is allocated to be shared amongst a thread block. All right, so the single threads are using registers. Shared memory is shared between a thread block, not a warp, a block. Okay, and this is typically used to do things like load global memory, basically, prefetch it to reduce memory latency, or also it's used for certain operations like reduction operations. So if you're coming from an OpenMP background, you have a reduction operator you just stick on your pragma. Well, if you're going to switch to CUDA or HIP-C++ kernels or CUDA Fortran kernels or what have you, you're going to use shared memory to use that reduction. You're going to have to write that reduction manually. I'm not going to go into how to do that in detail right now, but just know reduction, I need to use shared memory, and you can look it up later. All right. And then the highest level of memory, which is accessible by all threads on the device, is the global memory. And conceptually, this is the same as like RAM on a CPU, right? We have the global caches and the VRAM on the GPU, and it's not much different. The only thing to remember about the global memory on a GPU is this is what we can control from the CPU, right? We allocate memory in the VRAM with commands from the CPU. And of course, just like with any compute architecture in existence, the closer you get to the compute circuitry, the faster the memory fetching is, right? So obviously you want as much of your important data in the registers as you can without overusing the registers. And we could prefetch memory into shared memory to make this fetching of that faster later when we do our actual computations. And obviously, if we have to go all the way to global memory to get something that's going to be a slow operation. The reason we're so concerned with memory on GPUs is because memory latency is a big issue. Memory latency is a big issue on CPUs as well, but oftentimes you can get away with it. We have much deeper cache hierarchies, and the kinds of operations you're doing on CPUs, typically it isn't as much of a concern. On GPU, it is the concern, okay? That's because GPUs compute far, far faster than they load data. Far, far faster. Also true for CPUs, but even more true for GPUs, okay? And the way that we get around this for GPUs is we do what's called oversubscription, right? GPUs, as it says in big bold letters on the slide there, are throughput machines. They are made to be stuffed with as much work as possible, right? Their whole concept of GPUs is built around this idea, all right? Basically what the scheduler on a GPU will do is it will generate those warps, like I said. You'll request resources, it'll generate warps to meet the request, and it will start scheduling compute onto its threads. And as one of those threads hits a memory load, and it's sitting idling, waiting for memory, perhaps from shared memory or global memory to show up, it will unassign that warp, and it'll put one of the warps that is waiting to compute out onto the threads instead. Okay? And it will continue this cycle, uncountable times throughout a computation. The problem for GPU computing and when your performance declines considerably is when that scheduler goes to get a waiting warp and there is not another warp waiting there. And all of a sudden you have a warp that is out on the threads, idling, waiting for memory, not doing any computation. And this is bad, obviously. Idling is bad for performance. So GPUs are throughput machines. Remember that, all right? The way that we measure how much throughput we have is called occupancy. And this is simply the number of active warps we have, ratio of the number of warps that are active on the device, over the maximum number of warps that we can assign, right? Basically the number of threads that are running versus the number of threads that exist on the hardware. The biggest thing that limits occupancy actually though is typically not the number of threads you have, but the number of registers. I mentioned that before. If you are having an operation that takes up way too many registers, this is what's going to start limiting your occupancy, okay? Because there isn't enough registers for all the threads to run because the threads that are running are taking up all of the memory, okay? And then a concept that I'll introduce now, it's a little bit more of an advanced concept in GPU computing, but we're going to discuss it later for GALÆXI, so I'll mention it here, and that is streams. Okay, streams are a concept or a construct in GPUs that allow us to do multiple things at once. Basically, we have multiple operations that are independent of one another, and we can run them concurrently on a GPU using streams. Okay, what this does is it allows us to do more oversubscription, but it allows us to put more work on the GPU if it's possible. So here's a little profile of GALÆXI that shows kind of the timeline of a time step in our code. The little blue bars, if you're unfamiliar with NVIDIA Insight profiles, the little blue bars are the runtime of a kernel. And you can see here in this little chunk that I've outlined in red, we're using our streams to run concurrent operations and hide some operations behind a larger, more computational expensive operation. And I'll point out over here on the right our volume integration kernel, which highlights that issue I just mentioned before, where this kernel has a very high register usage. And that means that we can't run anything else on the GPU while this kernel is running because we don't have enough registers to run anything else. So thinking about register usage, this is an optimization level thing to think about, but you might run into it. You will run into it for sure, actually. And it won't be a mystery to you. You'll be like, oh, wow, look at all these registers we're using. That's why our performance is bad. Okay. I mentioned kernel most a couple times now. This is just the definition of a kernel, and I use this just to highlight again this idea that all of the threads that are running in an operation or running in a kernel run independently of one another. It's, I think, the second of the three times I'm going to mention that. Otherwise, a kernel in a lot of ways looks exactly the same as any other function in code you've ever seen. It just has a few special decorators on it. We'll talk about the decorators in a second, but the function call of a kernel looks a little different, and it looks the same now for both AMD and NVIDIA. Thankfully, AMD changed their stuff, so it is the same as NVIDIA now, and it looks like this. You have your function name, and you have your function arguments on the right over there in the parentheses, and in between we have this, I think they're called angle brackets. I think of them as greater than and less than signs. Whatever you call them, it's like three of them nested. And inside of them, we have what we call our kernel launch parameters. Here we specify our number of thread blocks we want and the number of threads per block. This is where we do that step that I mentioned earlier. We can also optionally specify a block of shared memory, right? We specify the number of bytes that will be shared amongst a block of threads in shared memory. And if we're using streams, we can give a stream ID for this kernel to run on. All right. And I show this here again for people who are maybe ignorant of CUDA or HIP C++, or perhaps are coming from an OpenMP background where, you know, obviously this stuff is automatically generated by the compiler behind the scenes. And now you're going to have to actually write this yourself. Okay. So writing a kernel in CUDA and HIP C++ is a very, very complicated topic that, and you basically, I can't teach you how to do it. I can teach you kind of what it looks like, which is what I'm going to do now, but you have to go do it yourself to fully understand. Okay, so I'm just going to give a brief introduction and then good luck. Okay, so we have a Fortran function on the left. This might be something that you see in your code. And yes, I know I haven't declared any of the variables. This is a fuse multiply add operation, something you see a lot in graphics computing, and it's something that GPUs are optimized for. We're multiplying an array by a constant, adding it to another array, and then storing it into a result. It's just a simple little for loop problem. And then the HIP CUDA C++ code for that looks like this. It looks very similar to all other C or C++ code, except for a few notable differences. One is this global decorator. This global decorator tells us that this is a GPU function, specifically one that is called from the CPU and runs on the GPU. And then you might sometimes also see or use the device function decorator, which is a function that is called from the GPU and runs on the GPU. So both run on the GPU. The difference is where they're called from. Okay, we launch a global function and then we call device functions from within other device functions. Okay. The function arguments are function arguments. They're the same as any other function you've ever programmed in your life. However, there's just 2 points I want to make about this. One, all arguments to a kernel are passed by value. And two, do not pass host memory pointers into kernels. It'll pass the pointer by value into the kernel, but if you try to access host memory on a GPU, the code will crash. You cannot do that. Okay. And lastly is this wonderful little statement here, one that you'll become incredibly familiar with. I call it the Lord's Prayer of GPU computing. It's a little Christianized, though. You can call it whatever you want, the core tenet, the mantra, whatever you want to say. Yes, you will write this line of code many, many times in your journey if you're working in CUDA or HIP C++. And this is a way we determine our thread index. You'll notice that we no longer have a for loop in this code, right? That's because the GPU is doing the for loop for us, right? The GPU has created an n number of threads for us and is going to run this kernel function n number of times, and each instance of that kernel will be independent of all other instances. So to determine our array index, we have to calculate a thread index, and we use that thread index as our array index, okay? That is a lot of action. I know it is. And this is, again, one of those things where you just have to do it and do it wrong a couple times to realize, oh, that's how that works. All right. This is just, again, so you see it. because this is going to come up again a little bit later when we talk about GALÆXI, which is actually right now. All right, I'm going to take another drink of water. I'm talking pretty fast, but I need to make sure I don't need to talk faster. We're doing all right. And so now we're going to take this very brief, very shallow intro to GPU computing, specifically the software side of GPU computing, and we're going to then apply that to our code, GALÆXI. So a little bit more about GALÆXI before we get going. GALÆXI is an open source, high-performance computing-oriented solver for the unsteady compressible Navier-Stokes equations. We use a high-order discontinuous Galerkin spectral element method to solve those equations. What that is, I'm not going to explain right now, outside of the scope of this talk, but if you're interested in that, it's a simple Google search away. As I said at the top, we have an original CPU code called FLEXI, which is written entirely in Fortran, and we endeavored with this GALÆXI project to port FLEXI to GPUs. We did that using MPI-aware CUDA/HIP C++. I say always CUDA/HIP C++ because we use the same code for both CUDA and HIP with a few things here and there that we use to abstract between the two. And I'll mention what those things are in a second. And a very brief and very disappointingly small summation of the many features we offer in GALÆXI includes things like runtime specification of spatial order or polynomial degree. We have many options for Riemann solver, split flux operators, things like that. Different kinds of I/O, post-processing, all kinds of things from that angle. And also for like very compressible flows with shock waves, we have a very fancy finite volume subshell shock capturing method, so you can do high-speed flows with this code. Okay, so we endeavored again to port this code FLEXI and make GALÆXI, right? To port this code to GPUs, and we started out in this process of making sure we port it not only to just GPUs but all GPUs. The first step you do is you create a list of all the possible ways you could accomplish this task, all right? And that exercise generates this list. It might look a little different for other people, but this is the list that we came up with. This list can be split up into a couple of groups. The first is the pragma-based approaches, which is basically now just OpenMP. I think it's a pretty safe statement to now make that OpenACC is dying out. So when I talk about pragma-based approaches, I'm pretty much only talking about OpenMP. We also have abstraction libraries. The problem with these from a Fortran perspective is that they are almost entirely C++ based. You also have OpenCL, which is like a graphics driver, kind of like that graphic shader kind of language. Also requires C. Standard parallelism, I wish it was better than it was now, and I will say it will be better in the future. However, in this moment, with the speed that the standards committee moves and the speed, more specifically, that compilers adopt the standard, it's not perfect yet. It is an option, but I think it will get better. And right now, I would just steer clear of it. You can also do vendor native languages. So for CUDA, for NVIDIA GPUs, there's CUDA Fortran, and it is really great. We have an original version of this GALÆXI code that uses CUDA Fortran. Unfortunately, AMD does not have an equivalent of that. There is no HIP Fortran, right? So really, we have a bunch of these things that require the Fortran to C interfaces, and really what this list for us Fortran programmers boils down to is this list. You have to make a decision between using OpenMP or biting the bullet and building a Fortran to C interface structure and basically using one of those C-based approaches. Okay, so I'm not saying OpenMP is bad. In fact, OpenMP is great. I used to use it for things, and it's great because it allows you to stay in Fortran. The downside to OpenMP is that I think it's sold as like the easy way out, like the lesser effort version. And I don't think that's true. I think that's also unfair to OpenMP and it gives people the wrong impression about it. I think it requires maybe not as much effort as the Fortran to C thing, but still quite a lot. You still have to do a lot of code refactoring. You still have to do a lot of optimization work. It is possible to get CUDA or HIP-like performance out of OpenMP, but the amount of hair pulling you're going to do to get there, I think makes it not worth it. So, I mean, you know where we're going with this. We obviously chose the Fortran to C approach. This is because C is more flexible. Once you're in C, everything is supported. There is nothing you can't do, okay? It's easier to get performance. Just basically writing a code, naively writing a CUDA kernel is going to usually be performant out of the box. You can screw it up, absolutely you can, but most of the time, it's going to be more performant than any other approach just as a baseline, okay? The problem is that just writing it naively is still a very high effort task, okay? So this is the drawback of that, but if you're willing to eat that effort, then this can be a very rewarding approach. So we went that direction, and I'm going to assume from now on throughout the rest of this talk that you are going that direction too, right? In fact, I've talked to many codes which start out on OpenMP because they like that it would be easier to do, right? And find that they ultimately go toward the Fortran plus CUDA or HIP route for either more performance, or perhaps OpenMP wasn't really meeting their expectations in some other way, whatever, right? We're just going to assume, no matter how you got here, that this is the decision you've made to go this route. So you've made that big decision. There's now a bunch of little decisions we have to make. Obviously, something that weighs into this usually is what kind of personnel you have. You know, what is your group skill set? What kind of timeline do you have to do this porting effort? And what is that porting effort going to look like? Okay, so what are your requirements? How much code do you want to port, right? Do you want to port the whole code? Do you only want to port like some very intensive routines? Do you want to keep CPU computations, right? Because CPU computations can be something that when porting to GPUs are either severely degraded or perhaps removed entirely, like destroyed entirely, right? How do you want to handle that? Do you want CPU still? Do you want to just throw it away? You have to make that decision. And also revisit again the possibility that you don't need to do any of this at all, right? Revisit the possibility that maybe there is a off-the-shelf solution that can be used instead, right? Again, if you're one of these codes that's just building huge matrices, finding eigenvalues and going from there, you might not need to be writing kernels. Okay, there might be another way for you to accomplish this where someone has done all the GPU porting work for you. Okay, just remember that. Some more design-oriented decisions that you need to make, things like how does the GPU dependencies fit into your build system? How are you going to handle memory, right? And this is honestly a really, really big issue because you have that Fortran to C interface now. You have the language barrier and the device barrier. And how are you going to manage that? Where are you going to allocate memory? Where are you going to store the pointers to device memory? Things like this. You have to think about that. How are you going to map the data in your code to the GPU hardware, right? Am I going to do one grid point per thread? Am I going to do multiple grid points per thread? One cell per thread? How are you going to do that, right? Are you going to have inter-GPU parallelism? Are you going to have MPI involved? Usually, yes. What kind of MPI? Are they huge all-to-all collectives? Is it point-to-point? Like, what is it? You know, think about this kind of stuff. And also, if you're keeping CPU computations, how the CPU code and the GPU code will relate to one another. Will it be the same code? Will it be different code? If it's different code, how will we split? Okay? So we take all of these questions, all of these decisions that you need to make to do this process, and I'm going to now kind of just basically go through how we answered all these questions in GALÆXI. Okay? So the big thing we did, right, is that we're going to change as little as possible. This is the baseline design goal for GALÆXI. We're going to take Flexi, the Fortran CPU code, and we're going to change as little as we can, okay? This means retaining all of our data structures, retaining the MPI parallelization strategy, keeping everything that is not a compute kernel, everything that is not doing number crunching in Fortran and on the CPU, and everything that is not, okay, I mean, yeah, everything that's not IO, everything that's not, all of the IO, all of the initialization, all of the finalization, all that stuff is going to run on the CPU, stay in Fortran, and then everything that is doing the real number crunching is going to be C++ code that runs on the GPU. A couple of other decisions we made, right? We did decide to retain full CPU support. We decided that we were going to map a single degree of freedom to a single GPU thread. And this showed to be the most performant way to do things, and it was a good decision. I'll prove that later. We went with GPU-aware MPI, and again, we did not change any of our original MPI strategy. What that is, I'm not going to go into in depth, but basically we kept it the same as all that's important. And also we decided to use those streams that I talk about, because the way that the DGSIM numerical method works, we can do a lot of things concurrently, which means we can layer this compute stuff, and I showed an example of that with a profile earlier. The problems with this, the problems with these answers to those questions is that, again, this is a very high effort thing to do. We have a lot of compute kernels in GALAXI/Flexi, and we have to do a lot of porting, okay? There's also the limitations of the hardware, right? GPUs, again, it's a very specialized hardware that can do only very specific things. And also we're introducing extra software complexity with that Fortran to C interface. And I can tell you from our experiences with GALAXI that those bottom two things, the GPU hardware limitations and the Fortran to C interface, are going to be the two things that give you the most nightmares. This is going to be, fighting those two things are going to be where all of your time goes. If you're scared about writing kernels, I can assure you that is actually one of the easier parts of this. So how did we conquer this most difficult part, right? This Fortran to C interface, this CPU to GPU interface, right? And what we did is we drew the line right here, right? We said everything that is in Fortran is CPU code, and everything that is in C is GPU code, full stop. In GALAXI, in the code base, if you're looking at Fortran, that is CPU code. If you're looking at C, CUDA, or HIP, or C++ or whatever, that is GPU code. End of story, right? This delineates things in a really nice way. It puts a barrier right in the same place, so we only cross one barrier, we don't have to cross two. And this really was it turned out to be a very good decision. Right? This turned out to be very convenient. Okay, so how do we conquer these things? The first thing we have to think about is memory management. Okay, so what we do is we wrap the CUDA or HIP C++ API in a Fortran wrapper, right? This is, done in other ways too, right? We're kind of reinventing the wheel a little bit here, but we're just doing it specifically for our code. And what we do is we take our multi-dimensional Fortran arrays and we allocate them as a 1D flat array on the GPU. We then store these these pointers to this allocated GPU memory in a hash map. We save a key to that pointer, and then we pass that key back into the Fortran and save it there. Okay. This is just, again, so we're passing only integers through that Fortran to C interface, which means that we can't screw anything up. We don't have to map Fortran strings to C strings. We don't have to map Fortran pointers to C pointers. It is a 4-byte integer. There is not a compiler in existence that cannot screw this up. It is simple. It's not pretty. It's not, elegant in any kind of software engineering way, but it works everywhere, every time. And the reliability we really love about that, okay? And what we do basically later on is we use these keys. We pass the keys back through from Fortran to C, and then we use those keys to retrieve the device pointers when we launch our kernels, okay? And I just want to point out a couple things. One, we decide which backend we're using at compile time. You'll see some C macros there that are used to split between either CUDA or HIP. This is how we obfuscate the vendor specific code, okay? And also I should note that I show an example here for memory allocation, that memory copies, device synchronizations, pinning, like setting devices for a certain CPU core, all of this stuff is all handled in basically the exact same way. When we actually go to do compute, we use a very similar structure. Again, on the left, you can see that use Excel equals Excel off. Basically, again, okay, have we compiled for CPUs or compiled for GPUs? If we compiled for CPUs, then we branch to our CPU backend, which we know it's our CPU backend, one, because we've tagged a little host thing to the function name, but we also know we're on the CPU because this code is written in Fortran. Right? Remember, Fortran is CPU code. So this is just, in our case, was the original Flexi CPU code and was just retained with a little bit of refactoring. Okay. For our GPU backends, again, we pass those keys. So we see D out and D in on the left. We pass those keys into C, right? We launch our kernel. You can see, again, a little, that invoke kernel language there in the top right example is an obfuscation where we basically hide the kernel launch syntax behind a macro, just in case it's different for different architectures. We use those keys to fetch out our device pointers. We pass everything into a kernel. And as you can see here, that kernel in the bottom right, very, very similar in structure to the example I showed earlier. The one thing I'll point out is that if statement in there, that if I greater than in total return line, this is a callback to that point I made, I think, on one of the first few slides about warps, where we always get a full warp. So because of that, it will oftentimes mean that your problem size will not nicely fit into the blocks or the warps that you get on the GPU. And you need to kick any threads that are out of bounds of your arrays. This is a kick me thing that people miss and people forget. Even me now forgets to do this sometimes, and I get a segfault error when I first test my kernel, and I'm like, oh, I forgot to kick the threads that were out of bounds. So I just make special note of that for this exact reason. So this is just a highlight of our strategy. I mentioned this briefly at the beginning, and this is just me emphasizing that we stuck with this philosophy, and that was that we start our computation, we do all of the memory allocation and solution initialization on the CPU at the beginning, and then we copy everything to the GPU, and then we start the actual time stepping. And the GPU does all of the work, and periodically, of course, we'll copy back to the CPU so the CPU can do I/O, but otherwise everything stays on the GPU until the end of the computation. And just those of you who are a little more savvy with this, we pin a single GPU to a single CPU core. So when we use MPI, we launch with the same number of MPI ranks as we have GPUs, and then we do our pinning in software. Okay, so we don't use Slurm or PBS or something else to pin our GPUs to CPU cores. We use either CUDA or HipSet device or whatever other backends we add in the future. We'll use their mechanism for that. And then also note that when we make MPI calls, again, we're using GPU-aware MPI, so we're using device pointers to do direct GPU to GPU MPI communication. Just to mention on how we use streams, I've covered this a couple times now. Basically, what we do in GALÆXI is we have 3 streams with 3 increasing levels of priority. We put our MPI communication on the highest priority stream. Basically, any operations that work on elements that are on MPI boundaries get done first, so that data is ready. So we can do the MPI communication, and all of the interior elements can be worked on while that MPI communication is being carried out, right? The lowest priority is then our large volume-wise operations, like our volume integration. These are done completely independently of everything else, so we can just have them sat there and sitting on the back burner, computing in the background, because they aren't bothering anything else. I will note that the figure on the left is a little out of date. It has that big red synchronization thing on the bottom. We don't really use many full device synchronizations anymore. We now use a thing called events. This is available in both CUDA and HIP, and I think also in SYCL. I'm not really sure. a couple other things as well. But basically what these events are doing is it allows you to attach a listener to a kernel. This listener can give you information about the kernel as it's running, but critically it tells you when the kernel is finished running. So we have kernel 1 that will take data A, work on it, and spit out data B. We then have kernel 2 downstream that takes in data B. We basically attach an event to kernel 1, and we say before kernel 2 starts, make sure that kernel 1 is finished, because that means the work on my input data to kernel 2 is finished. And this allows you to be very, very specific and very, very intentional about data dependencies between your kernels, which will become a huge issue if you decide to use streams. Okay? So the porting process we went through for each kernel, right, is this process right here. The first thing that we would do is we'd write a unit test for our CPU code if we didn't have one already. We had a few, but we have, I think, 4 or 5 times as many as we did when we started. We use this unit test basically to do nothing but, hold on to it for later, because it's going to be important once we start writing GPU code. Something that we also did was FLEXI is pretty old, 10 plus years, I think, right? And so we had a lot of buildup of things that, people would have liked to have done, but hadn't done because of time or whatever. And so we kind of took the opportunity to do that now. This may or may not be something that's appropriate for you. And there was definitely some cases in which we steered away from it simply because we didn't want to change too much. But this is something where if you're changing code already and you already wrote your unit test where you can revalidate your changes very quickly, maybe it's something you want to do while you're at it. Okay? The next thing you're going to do is you're going to refactor that Fortran CPU code to look like a CPU backend, right? Basically, turn it into the structure that I showed a couple slides back. You don't have any GPU code. That call to the GPU backend, it goes to nowhere right now, but it doesn't matter, right? You're just going to build that structure and then again validate using your unit test, validate using any test problems you have that exist, right? And once you have that, right, you're going to start actually porting to GPUs, right? You're going to take that CPU code that you've hopefully changed such that it kind of looks like a GPU kernel now, right? You've maybe done a little refactoring, a little fixing that you had stored up over the years, and now you're going to write your GPU kernel. And this is where we're going to do everything, the process that I've enumerated over the last couple minutes, right? Where we're going to do our allocations, we're going to build those Fortran to C interfaces, we're going to actually write our GPU kernel. And at the end, we're going to use that unit test we wrote at the beginning to make sure that our GPU kernel is generating the same exact answer, obviously within some acceptable tolerance, as the CPU code. So the question now is, does this work? Right? Did we get out of this what we wanted? And the answer is yes, of course, or else I wouldn't be talking to you about it right now. So just to kind of go through some results, for if there's any non-CFD people here, a Taylor-Green vortex is a canonical validation problem in turbulent CFD. There's the problem conditions for this problem here. An example of what the flow field might look like. This image is actually generated with FLEXI, but it would look the same in GALÆXI. And here's some results for some important turbulent properties. And as you can see, we're matching the reference data, DNS reference data, wonderfully. We're a little off the reference data, but the key thing here is that we're matching our CPU results from FLEXI exactly on all architectures, on CPU for GALÆXI, on NVIDIA GPUs, and on AMD GPUs. Okay, so it's accurate. I could show you more validation problems, more things that we've run with this, but this is as much as I'll show now. I'm going to move on to performance. CPU weak scaling is on the left. We run on a half a dozen CPU systems across Europe. Our weak scaling, once we get up into the tens of thousands of CPU cores, isn't terribly great. It's definitely a little bit worse than I think FLEXI in most cases, but we did kind of reorient some things in the CPU code because we we oriented the performance optimizations we were doing almost purely toward the GPU backends. And so we moved a few MPI things around to be conducive to the GPU stuff. And as you can see, that definitely worked for the GPUs because up to 2,000 GPUs on Lumi, we have more than a 95% parallel efficiency and weak scaling on GPUs. And it's really good regardless of the architecture, right? And strong scaling were great on both architectures, super linear on CPUs. This was something we also saw from Fluxy, so that's really great. And near linear on GPUs, and that's all the way up to 8,000 GPUs on Lumi. And hopefully even further in the coming months, if we can get access to some bigger systems, okay? From a time to solution and energy to solution perspective, if we compare node to node, right? So we have Mare Nostrum, so MN5 in Barcelona in Spain, and then Lumi in Finland. Our time to solution on one node for a problem with 16 million degrees of freedom is somewhere between 3 to 4 times as fast on the GPU, and we accomplished that in roughly half the energy consumption. So that's something we love to see because we get our results faster. It's something that everybody loves to see because we're more efficient and we're using less energy, which is great for everybody. Okay, so that's GALÆXI. I finished on time, which is really awesome. This is the slide where we thank the funding from the European Union Euro-HPC joint undertaking for funding this project. And I also want to thank Sally for organizing the talk. And I'd also like to thank all of you for coming today. I really hope this is helpful to as many people as possible. And with that, here is those QR codes again. If you'd like to look into what we have going on, again, our website is on the left and our GitHub page is on the right. I will caveat that GitHub page QR code with the fact that the current version of GALÆXI that I just described is actually not on there yet. An older prototype version of GALÆXI is there, but if you check back in a couple months, the new version will be there. We're just finishing up the publication on the new version, and then it will be up. All right.